All right, so in the previous lecture, we calculated the change in energy based on given values of Q and W. So the values of Q and W, Q meaning heat, W meaning work, were given. Now we're going to turn to calculating Q, which is heat, and work based on changes in temperature and volume. So let's first talk about heat exchange. Heat is the exchange of thermal energy between a system and its surroundings. So it's an exchange of thermal energy between a system and its surroundings. Heat exchange occurs when a system and its surroundings have difference in temperature. So if they have a difference in temperature, there's going to be a heat exchange. Temperature is the measure of thermal energy. Okay, so it's the measure of thermal energy, how much thermal energy is within a sample of matter. Heat flows from matter with high temperatures to matter with low temperatures until both objects reach the same temperature. This is called thermal equilibrium. This makes sense. When you're holding a hot coffee cup, the thermal heat from the hot coffee cup is going to flow into your cold hands, and then eventually they're going to reach thermal equilibrium. Eventually your coffee cup's going to cool down. Okay, so when a system absorbs heat, its temperature increases. Okay, so when it absorbs heat, the temperature increases. The increase in temperature is directly proportional to the amount of heat absorbed. So an increase in temperature is directly proportional to the amount of heat absorbed. And this is the proportionality constant, meaning the proportionality constant is called the heat capacity. Okay. Heat capacity, it's different for any type of matter. So each type of matter has its own heat capacity. That means it's talking about how temperature is increased and how much heat is absorbed. So the units of the heat capacity are in joules per degree Celsius or joules per Kelvin. So Q, heat, is going to equal that heat capacity times the change in temperature. So it's going to have that heat capacity, meaning each object has its own heat capacity, times how much the temperature changed. The larger the heat capacity of the object being studied, the smaller the temperature will rise. So the larger the heat capacity, the smaller the temperature will rise. So if they have a higher heat capacity, then the temperature is not going to rise as much. So the heat capacity of an object depends on its amount of matter. That makes sense. It is usually measured by its mass. 200 grams of water requires twice as much heat to raise the temperature by 1 degree Celsius as 1 degree of water. So this makes sense. 200 grams of water takes twice as much heat to raise 1 degree Celsius as 100 grams of water. Okay, it's proportional to, so the amount of temperature rising is proportional to how much you have. The heat capacity of an object depends on the type of material. 1,000 joules of heat energy will raise the temperature of 100 grams of sand 12 degrees Celsius, but raise the temperature of 100 grams of water only 2.4. So sand's only going to be raised 2.4, but sand's going to be raised 12 degrees Celsius, but water will only be raised 2.4, and that's because water has a different heat capacity. Water actually has a very high heat capacity. Okay, so let's look at specific heat capacity. So the measure of a substance's intrinsic ability to absorb heat. So in order to understand two important concepts related to heat capacity, imagine putting a steel saucepan on a kitchen flame. The saucepan's temperature rises rapidly as it absorbs the heat from the flame. However, if you add some water to the saucepan, the temperature rises more slowly. Why? The first reason is when you add the water, the same amount of heat must now warm more matter. It must warm the saucepan and the water. So the temperature rises more slowly. In other words, heat capacity is an extensive property. it depends on the amount of matter being heated. Okay, remember, think way back to when we talked about types of properties, extensive and intensive. Extensive property depends on the amount of matter. The second and more fundamental reason that water is more resistant to temperature change than steel is water has an intrinsically higher capacity to absorb heat without undergoing large temperature change. The measure of the intrinsic capacity of a substance to absorb heat is its specific heat capacity. The amount of heat required to raise the temperature of 1 gram of substance by 1 degree Celsius. So if you look on this table, this tells you how much heat is required to raise 1 gram of the substance 1 degree Celsius. Okay. The units of specific heat capacity, also called specific heat, are joules per gram degrees Celsius. This table lists the values of specific heat capacity for several substances. Heat capacity is sometimes reported as molar heat capacity, the amount of heat required to raise the temperature of 1 mole, not necessarily 1 gram, of a substance by 1 degree Celsius. The units of molar capacity are joules per mole degrees Celsius. We can see from these definitions that specific heat capacity and molar heat capacity are intensive properties. They depend on the kind of substance being heated, not the amount. Okay, so specific heat depends on the amount of substance present. How much heat is it going to require to raise this temperature? Now, specific heat capacity is intrinsic. That means that it does not depend on the amount of heat present. It depends on what type of substance you have. So lead, if we look at lead, we see that its specific heat capacity, this is in joules per gram. Again, it can be measured in joules per mole degrees Celsius. But it takes 0.1268 joules per gram degrees Celsius, 1.268 joules to raise 1 gram of lead 1 degree Celsius. That's what this means. It takes 1.28 joules. Takes 1.28 joules to raise 1 gram 1 degree Celsius. Okay. Now notice that these elements right here its specific heat capacity is fairly low. And that makes sense because they're all metals. Remember, metals can conduct heat very well. And so that's why its specific heat capacity is very low, is because it doesn't take as much to conduct heat, or for heat to travel through it. Now, compounds, ethanol, and water, they're a little bit higher. Water is very high. Okay, water is very high. It takes 4.18 joules as opposed to 0.1 to raise water 1 gram of water 1 degree Celsius. That is why water takes so long to boil. If you're trying to make some mac and cheese, you're going to have to sit there for about 10 minutes trying to wait for water to boil because its specific heat capacity is very high. And here's other materials. There's glass, granite, and sand, all of which can conduct heat very well. So the specific heat capacity, again, is the amount of heat energy required to raise a substance 1 gram 1 degree Celsius. Now it's measured in CS, that's our unit, or that's what it'll look like, specific heat capacity, because C is specific heat, and then the S is C is heat capacity, and the S means specific. It's in units of joules, grams, degrees Celsius. So, and molar heat capacity is just talking about the same thing, but it's the amount of energy to raise the temperature of 1 mole instead of 1 gram. So, molar heat capacity these numbers will look a lot bigger for molar heat capacity. Okay, so the heat capacity of an object is proportional to the following. It's proportional to its mass, and it's also proportional to the specific heat of the material. So we can calculate the quantity of heat absorbed by an object if we know the mass, the specific heat, and the temperature change of the object. Okay, where Q is the amount in heat, so Q here is going to be the amount in heat in joules. M is the mass of the substance given. CS is a specific heat. Remember, this is different for any type of compound. So for water, that would be that 4.18. For iron, it'd be that 0.1. And then the T is the change in temperature. Notice the temperature. Notice the temperature. It's in Celsius. It's not in Kelvin. So you got to be careful with that. Now, but degrees Celsius is equal to, you can interchangeably use degrees Celsius and Kelvin as long as they're all in degrees Celsius and Kelvin. But honestly, I do it in degrees Celsius because the specific heat's going to be in degrees Celsius. Okay, so water can absorb a lot of heat energy without a large increase in its temperature due to its high specific heat. Okay, so the large amount of water absorbing heat from the air keeps beaches cool in the summer. So if you've ever been to the beach, it always feels a lot better on the actual beach than, say, walking up to the beach. Walking up to the beach, it tends to get really hot, and then once you get on the beach, it's cooler. And that's because of the specific heat of water. It can absorb that much. So there's a temperature difference in the summer between Sacramento, which is an inland city, and San Francisco, which is a coastal city, maybe as much as 30 degrees Fahrenheit. So they're on the same part, kind of sort of on the same parts of California, but Sacramento's inland and San Francisco's on the water. That's why San Francisco can have a almost 30 degree Fahrenheit difference, because that water is absorbing the heat. Water is commonly used as a coolant because it can absorb a lot of heat and remove it from important mechanical parts to keep them from overheating. So water can prevent melting. It can also be used to transfer the heat to something else because it's fluid. Okay, so let's look at temperature changes in heat capacity. Suppose you find a penny minted before 1982, when pennies were almost entirely copper, in the snow. How much heat is absorbed by the penny as it warms from the temperature to the snow, which is negative 8 degrees Celsius, to the temperature of your body, which is 37 degrees Celsius? Assume the penny is pure copper and has a mass of 3.10 grams. Okay, so you're given the mass. You are given the initial temperature, which is that negative 8 degrees Celsius, and you're given the final temperature, which is 37 degrees Celsius, and we want to find Q. We want to find the amount of heat required. So the equation we're going to use is that Q equals M, the mass, times the specific heat times the change in temperature. So, and we're going to plug it in to solve for Q. And so here, if you notice here, the specific heat for copper is 0.385 joules per gram times degrees Celsius. I'm not going to make you memorize the specific heat. It will probably be given in the problem, and so you'll have it for the test. Okay, so it says gather the necessary quantities and then calculate for Q. So the change in temperature is 37 degrees Celsius, the temperature final minus the temperature initial, so 37 degrees Celsius minus negative 8, and that's a 45 degrees Celsius difference. So plug in the grams, plug in our specific heat for copper, and plug in the temperature difference, and that gives us 53.7 joules. The units, joules, are correct for heat. The sign of Q is positive, as it should be, because the penny absorbed heat from the surroundings. Okay, the Q is positive because it absorbed heat from the surroundings. Okay, it went from colder to hotter. Now, if it went from hotter to colder, that means that the final temperature will be lower than the initial temperature. Therefore, Q will end up being negative. And what happened is it put off heat. It gave off heat. Therefore, it's going to be a negative Q. Okay, so let's talk about thermal.